Welcome back, and we're going to start talking about buffers and pH regulation and how it's monitored in the body. So essentially, as you can imagine, with enzymes being so dependent on a particular pH, the body has ways of maintaining pH within a certain range. So the pH in our body doesn't tend to drastically change. It's actually buffered, which means it resists changes in pH. So we're going to have a look at that, and we're going to need to do some calculations with these as well. So make sure that you have your calculator to hand. Essentially, what we're looking at is that buffer systems are an equilibrium system, okay? So if we have an acid, which is shown here as being HA, a generic acid where we have a proton that is able to be donated, it's in an equilibrium system between being a H plus or H3O plus and A minus, its conjugate base. Okay, so as you can imagine, buffer systems are usually going to be combinations of weak acids or weak bases, okay? Because if we have strong bases or strong acids, then our equilibrium constant is going to be very large. The equilibrium position will sit far to the right, and we won't have a true equilibrium position. We're looking at equilibrium here, so we're looking at Le Chatelier's principles and ways in which it can be affected. Essentially, what a buffer system does is it means that small changes in pH don't have a large impact. What it means is that we can add acid or base into the system, and the system will resist changes as a result of that acid or base being added. So a buffer must always be made from a solution of a weak acid and the salt of its conjugate base. Okay, so it can be made from something like ethanoic acid, okay, and be in equilibrium with the salt of the conjugate base of the ethanoic acid, okay? So this is essentially what we're going to look at, these systems, and look at the equilibrium calculations that go along with them. A couple of things to remember is that we need to remember that pH is a measure of the acidity of solution, and it's always dependent on the concentration of H plus or H3O plus, okay? So it doesn't matter what's happening to the other things in the system, we're really focusing on what happens to the concentration of H3O plus. So when we look at the equilibrium system, there's going to be two systems present in the buffer. For the weak acid, it's going to be dissociating into H plus and A minus. And if we have a salt, we're going to have the salt with its, so the positive part of the salt and negative part of the salt, which are going to dissociate. Okay, so when we look at these, there's a couple of things that we need to think about when we're talking about approximations. This is that the dissociation of the weak acid, okay, so the going from the HA into the H plus and A minus, is so small that it can be considered to be negligible. That is, that at equilibrium, it sits far to the left, so that in any weak acid system, we're mostly talking about reactants and the products not being produced much at all. By doing this, we can make an assumption, and that assumption is, when doing calculations, that the concentration of the weak acid at equilibrium is going to be equal to the concentration of the acid initially. So if I'm doing calculations to work out the change in pH of a buffer system using ethanoic acid, I am going to assume that the concentration of ethanoic acid at the start is going to be equal to the concentration of ethanoic acid at equilibrium. Okay, so I'm not using Rice tables, so this is accessible for SL students. So we're saying that because there is so little, that the equilibrium position sits so far to the left, that we can make this assumption. The other assumption that we make is that the salt fully dissociates into ions. Okay, that is, that for the salt, we are dealing with CH3COO minus rather than the acid form. Okay, so these are two assumptions that we make. What we're talking about when we're talking about visualizing a buffer system is that we have this weak acid, which is going to partly dissociate, but mostly be towards the acid side. And then we also have the salt, in which case it's going to be mostly towards the salt side. So what we're saying is that in a buffer system, we have the acid present, but we also have the salt present. Okay, so one way we could do this is to take 100 milliliters of ethanoic acid and we could neutralize it with the half the amount of base. Okay, so if this was 1 molar, okay, I could add 50 milliliters of 1 molar sodium hydroxide, and what I would end up with is a 50-50 mix of the salt, CH3COONA, and 50-50 mix of my acid. Okay, so what I did was I started with a lot of acid and I neutralized half of it to get this mixture. And this would act as a buffer because now I will have an equimolar amount of the salt and an equimolar amount of the acid. Okay, so what this means is if I was to add in H plus to this system, okay, which would put the system under stress in terms of equilibrium position, the system would then move to the left, okay? Because it has a large amount of salt, it won't change my overall H plus concentration. The salt will be able to pick up this and reform CH3COOH. Because my H plus concentration won't have changed much at all, my pH won't have changed. On the other hand, if I was to add some base into this system, OH minus, it would react with the acid, okay, taking the acid out of solution, okay, and it would reform the salt. So in this case, the equilibrium would then shift. Both of these situations mean that we won't see a change in pH because the equilibrium shift won't affect the H plus concentration. So what we have, as long as we have base to react or acid to react, the H plus concentration isn't going to change much as the equilibrium position changes. Therefore, we won't see much of a change in pH. Let's see what this looks like mathematically. So, when we add acid, the pH initially decreases due to the addition of H+, then the equilibrium will shift due to Le Chatelier's principle. The backwards reaction will occur, consuming that H+ and returning the system too close to its original pH. With a base, the pH initially increases, but then the OH reacts with the H+ in solution. Okay, due to Le Chatelier's principle, because the H+ has decreased, the forward reaction will occur, recreating H+ ions in solution, which will drive the pH back down towards its original pH. Okay. If a large amount of acid or base is added to the buffer system, it won't be able to compensate for this, okay, because the change will be too high. But as long as we're adding fairly small amounts and there is sufficient weak acid or weak conjugate base present, then the system will be able to adjust and we will see minimal to no change in pH. How we look at these mathematically is using the Henderson-Hasselbach equation. All of these equations are given in section 1 of your data booklet, okay? So essentially what we need to do is remember our two assumptions, that the concentration of the acid at equilibrium is going to be the same as the concentration of the acid initially, okay, and that the concentration of the salt is high. Then we can look at these equations. Okay, so it's just important to note pK and pKb refer to the acid dissociation constant and base dissociation constant for weak acids and bases. There is a list of these in your data booklet, which means if you're trying to use these equations and you can't find the pK or pKb, then look them up. They have a list for common weak acids and weak bases in your data booklet. Okay, so you will often need to look these up in order to be able to do these calculations, and then it's just going to be a substitution kind of arrangement. Okay, so these equations are given in your data booklet. So the pH of a solution, of a buffer solution, is going to be equal to the pKa, okay, plus the log to base 10 of the concentration of the salt divided by the concentration of the acid. Okay, that's for an acidic buffer, so pH lower than 7. For a basic buffer, it's the pOH is going to equal the pKb plus the log to base 10 of the salt divided by the base. And remember that the pH calculations that we've seen before, we can still use, so pH is equal to the negative log to the base 10 of the concentration of H3O plus, and that the Kw is equal to the concentration of OH minus multiplied by the concentration of H3O plus, which is 1 times 10 to the negative 14 at 25 degrees C. So all those equations still hold here. Okay, and the pOH is essentially the same as pH, but this time looking at the OH minus concentration. So let's look at some of these calculations in work. So this means that we can determine the pH of a buffer solution as long as we have the Ka or Kb, because pKa is just equal to the negative log to base 10 of the Ka, okay, and pKb is just the negative log to base 10 of the Kb. Okay, so, and then we just need the ratio of the initial concentrations of the acid and the salt used to prepare the buffer. Okay, so we have all these equations. Let's see how they work. So this one asks us to calculate the pH of a buffer solution at 298 Kelvin, prepared by mixing 25 centimeters cubed of 0.1 molar ethanoic acid with 25 centimeters cubed 0.1 molar sodium ethanoate. So it's important to remember what our final, we're mixing these two together, so the final volume, okay, is going to be the sum of the two, okay, and then we're mixing the base and the acid. So we're given the Ka of ethanoic acid as 1.8 times 10 to the negative 5 at 298 Kelvin. So thinking back to our equations, okay, we can now go, if we have the pKa, so we know that the pKa is equal to the negative log to base 10 of the Ka, okay, which is going to equal 4.74, as we see here. We know that there are equal volumes and concentrations of the two, okay, so that means we can use the pH is equal to the pKa plus log to base 10 of the concentration of the salt over the acid, okay, and if these two are equal, okay, then the ratio of the two is going to equal to 1. So we're going to substitute in our 4.74, which is the pKa value that we worked out, plus log to base 10 of 1 is going to be 4.74 plus 0. So the pH of the solution will be 4.74 for a buffer made of equal amounts of ethanoic acid and sodium ethanoate. Okay, now we're being asked to prepare a buffer solution of pH 3.75, starting with methanoic acid and sodium hydroxide. So we're going to need to work out what concentration of methanoic acid will equal a pH of 3.75. So we go to the pKa, so a buffer with equal amounts of moles of this acid and its salt will have a pH of 3.75. Okay, so because the pKa is equal to 3.75, now going back to our previous question, remembering that the salt over the acid, if this is equal to 1, then the log to base 10 is equal to 0, so it will be the pKa plus 0 is equal to the pH. So what this is saying is if we keep the concentrations equal, then the pH will equal the pKa. Okay, so this means that equimolar solution prepared by reacting the acid with sodium hydroxide so that half of it is converted into the salt, we will get this situation. So essentially you would take what we talked about before, 100 mils of methanoic acid, and you would react it with enough acid so that half of it is converted into salt. Okay, so if you had 100 mils of 1 molar, then you would react it with 50 mils of 1 molar sodium hydroxide to produce an equimolar solution, and it would have a pH equal to the pKa, which was 3.75. Okay, so next example. How much 0.1 mole per decimeter cubed butanoic acid solution and solid potassium butanoate should be used to make 1 decimeter cubed of pH 5 buffer solution? State the assumptions made in the calculation. Okay, we're going to have to get the pKa of, well, the Ka of butanoic acid, okay, from our data booklet. The other thing that we're going to need to do is determine what concentrations we're going to be dealing with and what pH. So from the data booklet, butanoic acid pKa is 4.83. Okay, so we can now substitute this into the pH is equal to the pKa of the salt over the acid. Okay, so the pH that we're after is 5. Okay, and then we're going to then take the anti-log of both sides. Okay, so this is using your log knowledge from maths and take the anti-log of both sides. So we will get 10 to the 0.17 is equal to 0.1 mole decimeter cubed, which is going to equal 1.5. Okay, so then we can solve for the butanoate ion. Okay, so this is 0.15 mole per decimeter cubed. What we need to do then is work out the mass that we would use for these. So 1 decimeter cubed of 0.15 mole per decimeter cubed solution. Okay, we're going to need 19 grams to make this, and that will be added to the 1 decimeter cubed of 0.1 molars butanoic acid. Okay, if we think about it, what are the assumptions that we've made? Going back to those ones that we talked about when making buffers, we know that we have to assume that the butanoate ion at equilibrium is going to be equal to the initial concentration of potassium butanoate that we added in. We are also making the assumption that the butanoic acid at equilibrium, the concentration will be equal to the initial concentration, and that no volume change occurs on mixing the solution. So when we add in the 19 grams of potassium butanoate, it isn't going to change the overall volume of the solution. So these are 3 assumptions that we are making in order to be able to solve this calculation. Okay, if we didn't make these assumptions, there would be no way for us to solve these types of problems. Okay, what I suggest is you have a good attempt at these questions from your textbook, and we will spend a lot of time going through the calculations in class, as this is something that we need a bit of practice on. So have a go at these, and then we will look at some more and make sure to clarify anything that you're uncertain about the next time we meet.